Andrew Roberts. I'm from Naval Postgraduate School, and what I'm going to present now is something that I don't think my program managers would like me to say, but it's not explicitly been mentioned in our proposals, but we encountered something a few years ago that was a smoking gun for how we might represent porous ridges and perhaps change the way we represent sea ice thickness in models. So I'm going to present some heretical ideas, and hopefully you won't burn me at the stake in the next 40 minutes. One of those heretical ideas is that the thickness distribution as we currently use it in models is inadequate and is an inadequate representation of sea ice morphology, and we need to progress from using it. It's not quite right. I'm going to suggest a few really crazy things, like it is entirely possible for sea ice thickness to increase mechanically and for there to be no horizontal strain or strain rate. And I'm going to suggest that there are some new physics that have been developed by theoretical physicists that we can now take advantage of to get closer to at least begin to represent porosity, or the macro-porosity of ridges, the spaces between ridged ice blocks. I need to acknowledge my co-authors here who have put in a lot of work over the last few years. We've been working on this for 2 years. We're about to submit it, and we feel that it's ready for sharing. Particularly Elizabeth Hunke, who's been a great mentor and has corrected my mathematics on more than one occasion. Samy Kamal, who's a postdoc at Naval Postgraduate School. Bill Lipscomb, who's worked on representing sea ice thickness in models for many years, is now at NCAR. And Wieslaw Maslowski, who is the most patient man in the world. I'm going to start off by putting a slightly different slant on Drew Rothrock's work and Alan Thorndike's work and present it in a variational framework. And then introduce a principle of non-conservative stationary action that has been developed in recent years at Jet Propulsion Laboratory, and something that we can apply to sea ice models. The bulk of what I'm going to show you today is on a very small ridging model, just a very analytic ridging model that can be applied on the large scale in big models. And I'm going to briefly mention how we apply to large scale models. Rather than cramming this talk full of everything, I thought it was better just to focus on, particularly on this 3 and 4, on these results, because we've simplified ridging down to just a few equations that are quite telling of some of the underlying physics that perhaps we're missing in models. And I'd like to set the scene with this video that I took in the Beaufort Sea in 2007 of a ridge forming. So the colours aren't great, but what I want you particularly to hear is the audio. Listen to all of that energy being dissipated. Something that we often forget in sea ice mechanics is that the main game is not in sea ice getting thicker, it's in energy being lost from the system, 90 to 95% of the energy being lost from the system. And we often forget that point. That's the main term we're worried about. And you can hear lots of energy being lost in sound waves, in friction, and let's just let it build up here. We're about to reach a point of failure. So that was in the middle of our runway. Now, how did that happen? First of all, in the middle of our runway, this was at the Sedna Ice Camp, we had a flow, and a nice first year ice flow. It was about 1.5 metres, nearly 2 metres thick at that time of year. It was in March. How did it happen? Well, first of all, there was divergence, and our runway split in two, and we ended up with a nice lead in the middle of our runway. Not perfect. And then there was convergence. And of course, the compressive strength of flows is much larger than the flexural strength, and so it's very typical that the normal standard proceedings is that you'll have divergence or some sort of flow creation and then ridges created at the edge of the flows through flexure, through buckling. These are well-established principles going back for many, many years that buckling is a really important thing in ridge generation. Of course, flows can fracture in the middle, but it's quite a rare thing to happen. So it's nice to think about that because it's quite closely related to flow size distributions, something we'll come back to. We've seen these two equations that I inserted last night because they popped up so often, of course, the sea ice momentum equation and the sea ice continuity equation. I'm going to put a slightly different slant on it here. This isn't quite worked out typographically here, but I've put a slightly different slant on this. This is in material coordinates. Okay, and I'm just going to talk about body forces. You've already seen the air, water, and sea surface tilt terms that were mentioned. But the terms that we're particularly interested in here is the compressive strength of ice. And I'm representing a yield criterion with just one big F function because I'm not particularly concerned about it here. Okay, so this is the momentum equation as we currently use it. And this is our sea ice continuity equation. I'm not so concerned with thermodynamics in this talk, so I'm going to dump all the thermodynamics into this single theta term, and we're just going to be interested in the redistribution function, which Ken mentioned on Monday is highly nonlinear and quite a difficult term to come to terms with. So they're the two terms that are going to be of interest to us. But you're probably all familiar with Drew Rothrock's work in 1975, but this is a different slant on it. Okay, so this is in fact, just in a nutshell, in 2 slides, we'll be able to summarize Drew Rothrock's work in variational terms. We have virtual internal work density, and we're not talking about an energy density here, I'm talking about an energy per unit area of the sea surface. A virtual gravitational potential energy. And what I've done is separate these two terms out because the gravitational potential energy is path independent. That's the term that builds up, we build up sea ice thickness, and all we care about when we're travelling along a path, a ridge is forming, is what the potential energy is at the start and at the end. And it may go up in the middle and we don't care. All we care about is at the start and the end times Ti and Tf. And we've separated out the stress into a non-conservative and a conservative component. And this is the non-conservative component. And this term is path dependent and must remain inside this integral because we don't know what happens with it. It's really hard to come to terms with that term. And so what we do in models at the moment is we represent it as a multiple of the potential energy gain with this CF parameter. And the CF parameter is typically set to 17 in CICE. Michelle Samados and Danny set it to 21.3 for their anisotropic rheology. But in any case, it represents the fact that there is far more energy being dissipated than there is potential energy gain. So just think about that for a moment. In all our models, we are scaling a term that is 5% of the energy term. We are scaling 95% of the energy loss against a 5% term. Any small error in that potential energy can potentially yield large errors in our energy loss. There is good foundations for this, however. This is based on Mark Hopkins' finite element modelling. And so this isn't just been plucked out of thin air. There is some quite good basis for this. I'm just giving one example of Mark Hopkins' work. Danny showed an animation from it yesterday. But in a nutshell, this is what Thorndike and Rothrock did in these two papers that went together. And what we're interested in is the ridging of this area of the sea surface. And within this, there are lots and lots of paths. This is a continuum. Lots and lots of paths from xi to xf. Just I'm choosing one path here. And that's all ridging into another area on the sea surface. But in order to represent that potential energy, there were some simplifications made. And that simplification is, there's an implicit mapping function here of this much larger state space of sea ice. So I'm giving it a Gothic G here. And that state space includes the porosity of sea ice, the salinity, the enthalpy, and the thickness of sea ice. It's a much larger state space, but where do you start? If you're back in the 1970s and you're trying to build your first basin-scale model, I'd make that simplification too. But I'm going to suggest to you today that that simplification has some dire consequences for models, and we shouldn't be using it anymore. So on top of that, but if we make that simplification, we're able then to represent the change in potential energy quite easily using this ridging mode, and also the compressive strength of ice. So this term I'm circling around here is in fact just P there, the compressive strength of sea ice. And we've got our CF parameter here, so we're going to set that to 17. This is the difference in the water and ice density. This is ice density, this is water density here, the gravitational constant. And this is our thickness squared. And this is our ridging mode. Okay. And we're presenting it slightly differently here. We're presenting it in terms of we have a subspace of sea ice in an area that's ridging. This is AHI at the initial time, and that ridges to another subspace that's smaller and thicker, AHF, at our final time. But there's a fundamental problem with this. Non-conservative systems are initial value problems. Conservative systems are time-bounded value problems. We can represent in terms of the initial state and the final state. We shouldn't be doing that with a highly non-conservative system. But how do we get around that problem? Before we get to getting around that problem, let's also be aware of what is underlying our momentum equation that you've seen, because underneath that is a whole lot of Lagrangian mechanics. So let's stem back to conservative systems for a moment, just to make sure, and this might be in the distant memories of some people's graduate studies, so I don't mean to patronise my audience, but also want to make sure that I'm not jumping too far ahead. So there's a thing called Hamilton's principle, published in 1835 and 1836, and it's quite a simple idea that there is, in a completely conservative system, there is a minimisation of the action, the change in kinetic energy to potential energy over a path. So in simple terms, if you have a particle travelling from here to here, it's not going to do loop-the-loops, because that's not efficient at all. It's going to travel in the most efficient path from here to here, providing energy is conserved. But our energy isn't conserved. Nonetheless, through the principle of virtual work, we still have to assume that stationarity to come up with a momentum equation, which is what we're using. So underlying all of our sea ice models, whether you know it or not, is this assumed stationarity. Here's our body force, and we've taken x here as inertial. This is our reference frame, and so we can pop out Coriolis force. We can distill all of that. Let's just throw all of those body forces away, because all we're really interested in is ridging, which is just these terms here. And so this is our currently assumed stationary principle for sea ice ridging. Now we probably don't know we're doing it, but we are. So just to be clear here, so that I don't want to lose the room in case variational principles are in your past distant memory, what this is saying here is this is a functional. We're analysing a functional, which means that we're not analysing a function at every point in time, we're analysing its whole path. So the path from here to here, and the most efficient path is the one that's being chosen. And so we have this delta x term, this is the variation of it. And what that means is the term inside here, the integrand must also be 0. So it's variational calculus. What are the problems with those assumptions? Well, one of the problems for a start is that when we're scaling it, when we've decided to use this thickness distribution to represent the potential energy of sea ice, we have to assume all sea ice is isostatic, at least as it's being done at the moment. We're assuming that sea ice is path independent, and it's not. And we're assuming that ridges are equally as porous as the ice around them, and it is definitely not the case. So here's some pictures I took in the Beaufort Sea in 2007. This is Jenny Hutchings, this is Jackie Richter-Mengi, and Jenny's standing in front of what is what Arctic law would call a pressure ridge, and this is a shear ridge. There's no actual taxonomic distinction of those in any glossary, but so you can see this is very blocky, and this is all mangled because it's been formed under a lot of shear. And what you can see, of course, is that it's highly porous. In fact, it's really porous. So judging the porosity of ridges is really quite hard, and it's often done with incisional surveys, people drilling down or digging down and estimating the porosity. It's often not so objective, but there is some nice compilations in the last few years of porosities of ridges. I think that the nicest work I've seen is using nuclear magnetic resonance to get the porosity of ridges, so the keels and the sails. And this was published in Annals of Glaciology in 2013. But look at the numbers here: 40% porosity, 30% porosity in the keel. That's really significant. It's 1/3 of everything is water in here, assuming it's very permeable. Moreover, there's been some other work recently published, a really nice publication here showing that with all of that sophisticated trying to represent the potential energy to calculate the compressive strength of sea ice, it turns out that if you were to take Bill Hibbler's 1979 pretty basic parameterization of the compressive strength of sea ice, you end up with a better result in this particular model than doing all of the physics on it. And so this means also that our redistribution function, which is related to this ridging mode, has also got problems. There is another way to do this. Chad Galley at Jet Propulsion Laboratory has published 2 really nice papers. This one in Physical Review Letters in 2012. It got quite a write-up of the classical mechanics of non-conservative systems, and he came up with a stationary principle for non-conservative systems. And it goes something like this: that we can't really learn much about a system when we're just analysing an individual path, because this path could be going all over the place. But we can learn a lot about a non-conservative system if we analyse many paths together. In a field, it'll be many. I'm just going to use 2 today to keep it simple. And what we do is represent it with this non-conservative Lagrangian. So this is so what this is saying: non-conservative Lagrangian is composed of the conservative Lagrangians along these paths. That's the kinetic energy minus the potential energy, and then there's glue that glues them together, this non-conservative potential. And in sea ice, this is how it manifests. This is the stationary principle that we're all assuming right now, and this is the stationary principle that would apply with this new stationarity. Okay, and you can see that we have 2 different paths. We're looking at the stationarity of 2 paths in relation to one another. And what we're interested in is what happens in the limit as one of those paths goes to the other. As they converge, we're able to learn a great deal about the system. And we're going to keep it really simple today. We're just going to stick with the compressional axis, just to get an idea of the compressional strength of sea ice. And just analyse the system in a static state, which is how you analyse the compressive strength of any material. But if you see it all written up in textbooks, the compressive strength in static states usually is analysed for an elastic system because it's conservative. But the important thing is that when we do this, we have this simple Euler-Lagrange equation here, and we have this non-conservative potential here, and this is our non-conservative force. And that can be approximated like that to a 3rd order. So how can we do that? We're wanting to do this over a large area, over an area that could be 10 kilometres wide in a model, or it could be 1 kilometre discrete element in a model. This applies equally to discrete element models as it does to continuum models. And one way to do this is with coarse graining. So what we want to do is represent individual ridges as little quanta in our model. So we're going to dispose of all the complexity that we know exists in an individual ridge and try and just capture the physics of that and then be able to represent it on the large scale. And so this technique's often used for protein systems. It's not new, but it hasn't really been applied to sea ice a great deal. And we're going to do this with very, very simple polygonal structures. Okay, but we're going to apply a few important rules here. Before we apply those rules, I've just listed a fraction of the really important previous work that's been done on ridging. There is a rich history to choose from that helps to guide the choices we've made. So we haven't just drawn a few triangles and, yeah, that's fine. There is a reason for doing what we've done. And going back to the work of Makarov and Zubov in the earlier part of last century. And so we have a system of 14 equations that describes this. We observe Archimedes' principle for the entire ridge, not for individual bits of ice within the ridge, just for the whole ridge as a block. It conserves volume and it conserves mass, has geometric constraints. And this morning I rushed in this term because I thought Ken Golden's going to really worry about the permeability of the and so we're going to assume it's really permeable. Okay, so this is really, really simple. And that's why I like it, because it turns out we can learn quite a lot from analysing this very simple system. We have boundary conditions, which is our ice feeding into the ridge. And absolute certainty is that the thickness of the ridge right at its edge is the same as the thickness of the ice feeding into it. Absolute geometric certainty, and one of the few in ridging. And the snow and the shear is imposed as a boundary condition. And within it we have a strain, an angle of repose, and a porosity. And all of these are free variables. So this sort of thing is used a lot. It's used, Danny's group uses it for form drag, a ridge shape like this. Canadian groups are using it for land fast ice. It's used a lot in satellite analysis and aerial analysis of ridges. What's different here is these are all free variables. We're not using observations to say, oh, we'll constrain this or we'll constrain that term. We're just going to leave it all free. And we're going to let the variational principle determine what's right. And it produces some interesting results. So here's actually a plan view. It doesn't have to be like this, but I'm just going to represent this. Some things that begin to bend your mind a little bit about what should be happening. So this is, all of my figures now are to scale. They are the physics. They aren't just schematics. So they are, and this is to scale as well. So this is a flow that's feeding, you can see the original outline, and it's compressed together just by this amount and this amount, but this is the edge of the ridge that forms. It's in fact much larger than you would expect. This is what happens if we add some shear. So these two plates are still converging, but the ridging line is at an angle to that. And what happens is the ridge just becomes steeper, but in its compressional cross-section, it's the same as this one. Now, it might seem like a bit too simple to use this polygonal structure. In fact, it's quite general. In the background here, I'm plotting randomly generated structures of ridges that only have one thing in common with the Euclidean, the polygonal structure here, and that is these points here. So they all just meet these points here, but everything else of them is different. And so this is just a frame to represent a ridge. So it's actually quite general, much more general than you'd expect. And we can represent asymmetry with it. So we don't have to assume it's all symmetric. The one thing we are assuming is that the sail is over the top of the keel. Well, that comes from Parmeter and Kuhn's work. That suggests that when we reach an isostatic state, that's typically what happens in a ridge. Now, that's an important point. We're not going to represent in the mechanics the development of the ridge. All we're representing is the final static state that it reaches, because that's what's important for compressive strength and in a time step of a model. So how does this compare with submarine observations? Well, not badly at all. So this is Davis and Wadham's great work. This has 729 ridges analysed. It's the largest ever survey of ridges done here in Cambridge back in 1995, or published in 1995. And over the top is our morphology. Now, Davis and Wadham suggested this might be an exponential relationship. It's not. It's a cotangent relationship. We're able to fit it perfectly with our model. That actually just pops out of their geometry as well. But here's the most important result from doing this. Nice, simple model, easy to understand, okay? What I've set here is our ridge space here, and we've strained it by a third here, and we've got 2 metre thick ice feeding in at the edges, and here you can see the height of the sail, the depth of the keel, and the length of the ridge. Okay, so in this figure here, I'm going to increase the strain. I'm going to expand it out. It's going to be a half now. We've increased it to a half. You can see, as you would expect, to increase your strain, pushing in more ice, your ridge increases in size. But wait, what happens if we don't change our strain here, but we increase the porosity by 20%? It does exactly the same thing. Porosity behaves much like strain, and it has similar effect of a similar magnitude, and it is completely ignored in all known basin scale models. Let's take this example. We haven't strained it at all. All we've done is increase the porosity by 20%, and we've created a ridge. Is that physical? Absolutely, because the energetics are doing the right thing. We have two plates forcing against each other. They shatter. There's an energy of fracture. It consumes energy. Potential energy is gained. It just so happens that all of that space is filled with voids. It's quite improbable, but entirely possible to happen. And it's entirely impossible in all known basin scale models. So if we increase our porosity from 0 to 0.2, there's 78% expansion in the ridge width, 38% inflation in the keel depth. So this is important because currently in where models are using these really sophisticated great things like form drag and fast ice, and they're having to apply a porosity after the fact, after we've generated the ridges and the thickness distribution inside the dynamical core of the model, which doesn't include porosity. And so we're artificially expanding on top of what the dynamical core is really telling us is happening. And we're able to generate a nice simple thickness distribution from that, analytically. So this is our base state we had here, and these two states here, the thickness distribution, but this is the porous case here in purple, and this is the increased strain case. And this here is the case when we've just increased the porosity of the ridge. This is the thickness distribution just across the ridge. So this case, the purple case, is completely impossible in current models. And so we're forced to make a lot of assumptions about it. What happens when we increase shear? Well, that's quite a simple thing. You can see here that this shear ridge is really steep. Okay, when we shear the ridge, the same thing happens here. It becomes steeper when we're analysing on the cross section. But on the compressional plane, it's actually the same width. And we can dispose of other things. We can dispose of keel and sail shapes and things. They don't really matter. We can dispose of snow. So what happens? How do we represent the mechanics? This is the important part. So we want to come up with a nice simple model for mechanics, and so we're going to do this. We need to represent this Euler-Lagrange equation, and we're going to do this using Coulombic failure, not because it's the best thing to do, but because it's nice and simple and we can understand it. So it's coarse-grained, and we're going to assume it's cohesionless. And this has already been done by Mellor back in 1980. This is actually a case of two retaining walls against each other. It's a nice simple case, and between them there is a coefficient of passive stress. Okay, and so we have this Kp term here, and it's geometrically related to the angle of repose. But how do we set that? We set that using this new stationary principle, because rather than just analysing one ridge, we're going to analyse two together, merging together so that all those paths converge, and so our virtual potential energy converges, and Kp1 goes to Kp2, this compressive strength. So that condition is met. We end up with a Kp being constant when our internal stress with respect to angle of repose is 0. And so we end up with this Kp equals 3, which happens to be 10 times the UPC constant for sea ice. I'm sure you're all familiar with the UPC constant. No, the universal Perovich constant, 0.3. So this is Kp is this. So Hopkins came up with values between 2.4 and 4.6 for finite element modelling. Completely analytically, we come up with a value within that range. So this is where it begins to get kind of interesting. We're able to reduce the state space. It's often been assumed that ridges are all completely random. They are much less random than you might expect because of this variational principle. We've been able to completely reduce the state space. Now, we are constraining the angle of repose, but we're doing it variationally. And we're doing it based only on our initial condition, which is the state of the ridge starting at 0 strain and 0 porosity. And it follows these planes. So each one of these leaves here is for sea ice of a particular thickness feeding into a ridge. So if we follow this path here, this red path here, it's an entirely plausible path for sea ice to ridge. Don't worry about porosity going to 0.9 right now, we'll get to that. So you can see there's different paths here for ridges that can be taken on these planes. Okay, and what you can see in the background here, the colour is the angle of repose. And look at the values it's producing, around about 22 degrees, 24 degrees, 18 degrees in here. Guess what sort of median values are, or the, sort of the typical values, 18 to 22 degrees for a well-developed ridge. It's surprisingly predictive. And let's follow these paths here, just to have a look at what, we look at these pink, blue and green paths here. We can see this is what those ridges look like. They're all slightly different, all different shape, and they've got different porosities and slightly different keel depths, but they're all energetically identical and equally as probable to occur in the pack. Oops, sorry. Okay, so let's get to the point of the talk, hopefully not too late. And it's just in one slide. You need to do all of that work in order to get to the holy grail of representing porosity in ridges. This is our variational principle that we started with, that we're assuming in all models. Now, this still applies, the overarching variational principle still applies, because in the final state, our different paths have converged together. But we now have this term we can wipe out. This is our change in stress within a ridge with alpha. That can wipe out. And so now we're left with just our state space in terms of strain and porosity. And this is where this new physics development is really important, because without it, we can't begin to get an idea of the approximations we have to make to represent porosity. So I've just grabbed a leaf, just a part of our manifold just saw earlier, and you can see this white line here. These are observations of keels. This is maximum observations of keel heights and sail depths. They fall roughly on this line here. And what we're trying to find is the approximate path through the system. Now, this isn't an easy problem. Finding paths through a system was arguably the largest problem in quantum mechanics in the last century. And this is a really hard problem, but we're able to get at it by using, some history in it, by using this non-conservative potential. So to a first order, we can say that that path that I just showed up here is about right, and it predicts between 0.2 and 0.4, and for a ridge that is observable of porosity. That's about what's observed. But there's not that many observations of ridge porosity. A lot of them are subjective, so we have to go through tables of values. But it's predictive of this porosity. And so if we follow that path along, we end up with this, what I call this is the most probable plane of a ridge state. Okay, so what I'm showing here is the flow thickness that goes into a ridge, and this is the strain. And for every single point on here, it's predictive of a state of a ridge. Its shape, its porosity, its angle of repose, everything can be plucked out of this. But you can see that when a flow deforms, it's capable of all sorts of strains within our area. And that's a really useful thing to happen, because, let's go back, that within our area, there's only one assumption we can make to predict sea ice morphology, and that is that energy is equally distributed through that area. We can't assume anything else in a grid cell of a model or in an individual finite element. And when we use that, we're able to pluck out the large scale, keep going to here, the large scale distribution of ridge shapes, ridge separations, and everything else to do with the ridge. But The ridge separation is a really important part because magically a power law pops out. Let's go back to how ridges form. They form at the edge of flows. So we end up with a power law produced for the distribution of ridges, the separation of ridges between themselves, or the separation of flows in convergence. Yeah. It wasn't that important anyway. So let's don't be rude to Max. Magic. Okay, so within the time I have available, they're the really important points I wanted to take home. I skipped over the large scale and the equations to do it because what I really wanted to show you that we're able to come up with a nice ridge model that can be applied to the large scale, and it's really computationally efficient. It involves solving a biquadratic equation, which is really efficient to do for that plane I showed you, the most probable plane of ridges. And we're now able to get at this idea of macro-porosity. So instead of using a thickness distribution in sea ice models, we can now go to using a distribution that includes porosity. And bear in mind, this is what observers see. They're just measuring the top of the ice to the bottom of the ice, which includes all that porosity. In models, somehow we're representing some mangled, squashed up version of that doesn't include porosity. And that's the main game, right? This is where all the collisions are happening and all the energy is being lost. We don't have to presume that sea ice is isostatic everywhere. We don't have to do that if we apply the Euler-Lagrange equation, and we are careful to make sure our stationary principle applies everywhere within where the energy is being changed. And so we're able to get out a new redistribution function that can be used in a model and the compressive strength of sea ice. And so our next stage of this work is to implement this in CICE. And so there will be a porosity distribution and a ridge shape distribution that follows the sea ice around. And this is hopefully going to be useful for form drag. That was the original motivation for doing this. There are lots of other applications. We now have porous spaces that we can do biogeochemistry in. We now have the ability to compare this directly with satellite altimeter estimates of sea ice freeboard, because we calculate freeboard as part of this for individual ridges. They're just two applications, and given the time, I'll leave it there and take your questions, and thanks for listening to me.
Okay, thanks for this very nice talk. Can take maybe 2-3 questions. Oh, Danny, I was sure you would ask a question.
Well, there are loads of questions I could ask. So, in the form drag model, we currently assume constant porosities for the ridge and the keel, right? Yeah. So what is the range of porosities you get out here? Because if it's a narrow range, we could just continue assuming constant values.
No, it's between 0 and 40%.
Okay, it's quite a big range then.
Yeah.
What's kind of more interesting is the power law, well, given that that's important, is the power law distribution of the spacing, because that has a big impact on the form drag as well.
Yeah, and actually I'm glad you asked that question. So one thing I didn't mention is that ridges are not spaced with a power law. When you observe them, it's a log normal distribution. But we're not looking at a history here, we're just looking at a snapshot in time.
Say, we look at the fossils of the past, we realize.
And so the only way we can actually gauge that part of the model is when we apply it to SICE and we start to generate a history in the model. So.
Thanks very much.
I wanted to mention about this because you use plastic model for to determine energy dissipation during region events, but I think that in reality dissipation is going in many cases due to the friction between train of ice block running on the ridge sail or below the rich keel. So, and it gives less dissipation, so therefore you can get bigger rich size. So then in this model, rot rock, and they use this stage. Then Mark Hopkins already he discovered from discrete element that it is due to the friction. But another thing that there is limit size of ice ridges that because you only show triangular ice ridges, but there is ice rubble, and I think that's important that the ridge will not grow up to very big values, and that was discussed by Max Kuhn. So then it reaches some critical value, then it extends, and when it extended to the side, so then a sail to keel ratio will be different. So but if you parameterize, of course, and you have distance between ice ridges and you have ridge shape, of course, from law of mass balance, you can calculate everything if you prescribe some value of porosity.
So I think I got 3 questions from that.
That's just discussions.
First of all, I'm going to approach the maximum ridge height. That drops out of the physics. So that line here, we're not imposing that. This is a logarithmic scale. It's incredibly improbable. You can see this asymptotes. It's incredibly improbable for really big ridges to form. Yeah. They are possible, but I calculated this, they're about 10,000 times less likely than a ridge this size, depending on flow size and sort of. So it just drops out of the physics. We don't impose anything, but you can see this line here. There's a lot of ridges that take place in here and very few that will cross this observed line of maximum thickness. The next thing I want to address is the friction. Okay, it's a very important point that we're not representing the full evil. If you want to represent compressive strength of sea ice, that is a statics problem. Compressive strength of any material is a statics problem. It's when it's all progressed to its final static state. And so all we're interested in that final static state is what's holding the system together. It's interesting because the system is non-conservative then, but it's also non-dissipative, which is why we can't use Lord Rayleigh's principle of reduced dissipation that he came up with in 1871. That's why we can't use it, because we're in this static state where the system is both non-conservative and non-dissipative, right? And so all we care about is the mechanics of that final static state if we're calculating a compressive strength. Okay, and so I totally agree that this particular ridging model is simple, deliberately so. So there's also the things we haven't included that.
Good, but ridges are formed not along all contact line, but in places of stress concentration. So therefore, compressive strength of ice is much higher than stresses which are necessary for the formation of ice ridges. And from experiment in ice tank, for example, in Helsinki, it was shown that in initial stage of ridge initiation you may get high stress, but then when ridge is built up, so then stresses are much lower, and then they again reach some critical value of stresses when they are already big.
Okay. Guys, it sounds like a coffee conversation. we're getting late, so I would suggest, I don't know what you think, to go and get coffee, otherwise the schedule is going to get mad. Those who are interested, just meet with Andrew. Congratulations to the 2 speakers.